In this lecture, we will be considering Hooke's law for a two-dimensional angle lamina. In such a lamina, the fibers are inclined with respect to global axis. I can show an example. Consider an fiber reinforced lamina composite body, but the fibers are not unidirectional, they are not straight, and they are inclined with respect to the horizontal direction. These are the fibers, and there's an angle between the fibers and the horizontal direction. Therefore, the body is reinforced in both directions, in these orthogonal directions, x1 or x and y. And we are going to define coordinate systems for this case. Suppose that there's a global coordinate system as shown here, consisting of y and x axis. These are global axes, but we are naming these axes as y and x axis. And the local axes are defined in accordance with the fiber orientation. And this is, or these are the local axes, axis x1 and x2. And these are named as x1 and x2 axes. There's an angle of inclination is going to be shown as the angle theta. That's the angle theta. Now, fibers are aligned, therefore the elastic properties have relatively large values in both x and y directions. We know that in a unidirectional lamina, the elastic margins in the direction perpendicular to the fiber axis is not that large. However, by using an inclined orientation, you can introduce reinforcement in these two directions. We follow a certain notation here, x and y. These are referred to as global axes. X and y are global axes, and 1 and 2 are therefore called local axes. 1 and 2. We can refer to these as local axes. Now, from orthotropy, we know the relation in the 1-2 system. This is valid for the 1-2 system. And 1-2 are principal axes of orthotropy, actually. These are at the same time principal axes, principal axis of orthotropy. Therefore, original relations are valid in this coordinate system. But how can we find the relations in the global coordinate system? That's the question. How can we find these relations in the global coordinate system? So we will derive these. And for this purpose, we will first consider transformation. Of stress and strain. Strain. we are going to apply transformation formula in the derivations. So our coordinate systems, or we can show the coordinate systems one more time. These are the global axes, and x and y, 1 and 2 are the local axes. These are global, and 1 and 2 are the local axes. The angle of inclination is known. This is theta. Now, in strength of materials, you know how to evaluate stresses and strains in an inclined coordinate system like this. Suppose that stresses are given in the original global coordinate system, and you would like to find the stresses in the local coordinate system 1, 2. You can apply transformation formula from strength of materials, actually. Recall the transformation formula for this planar case. Transformation formula from strength of materials. These are given in your strength of materials book. Sigma 1 stress in one direction is sigma x plus sigma y over 2 over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta from strength of materials. Or more short analysis, I'll give you stresses in the 1, 2 system. Sigma 2 is sigma x plus sigma y over 2 minus sigma x minus sigma y over 2 cosine 2 theta minus tau xy sine 2 theta. And shear stress can also be calculated. Tau 1, 2 is minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. But we are going to express these transformation formula in matrix form using these trigonometric identities. Cosine 2 theta equals cosine square theta minus sine square theta. Sine 2 theta equals 2 sine theta cosine theta. And cosine square theta plus sine square theta equals 1. You can rearrange the set of equations and write them in matrix form. This is going to be the matrix form. Sigma 1, sigma 2, tau 1, 2. Stresses in the inclined system equals a transformation matrix T times stresses in the global system, sigma x, sigma y, tau xy. That's the matrix form. I suppose that this is equation 1. T is named as transformation matrix. This is called transformation matrix. And we know the elements of the transformation matrix. These formulae can be used. Tau or T, the transformation matrix, is this form. The elements, C squared, C is cosine theta, S squared, S is sine theta, 2SC, S squared, C squared minus 2SC minus SC, C, and C squared minus S squared. Here, S stands for sine theta, and C is cosine theta. And the inverse relation is also required here. Inverse of this, you can write the inverse relation as global vector sigma x, sigma y, tau xy equals T inverse times the local vector sigma 1, sigma 2, tau 1, 2. And T inverse can also be simplified. I'm going to write T inverse as well, but let's label this as equation 2. This was equation 1. Inverse is equation 2. And T inverse can be written in a somewhat simplified way. T inverse of transformation matrix is C squared S squared minus 2SC minus 2SC S squared C squared 2SC SC minus SC and C squared minus S squared. This is transformation of stress and strain. And we can derive stiffness matrix and compliance matrix in the new system or in the global system. First, we will write or find transformed reduced stiffness matrix stiffness matrix. We will see how this is obtained. We have said that 1 and 2 are principal axes of orthotropy, so our original relations are valid in this coordinate system. In other words, we know that for the orthotropic system, sigma 1, sigma 2, tau 1, 2 is stiffness matrix Q times strain vector 2, gamma 1, 2, and it's 3. And this is in the local system. We know that this is valid in the local system, and substitute this into 2 here. This result, transformation formula. Substitute or substituting into equation 2. There's one again. You will write global stress vector sigma x, sigma y, tau xy as T inverse times local vector T inverse, and this is the local vector. Therefore, we have Q times epsilon 1, epsilon 2, gamma 1, 2. But right side should contain the global terms, and we need to consider transformation of strains at this point. Same transformation formula. Applies to strains. I write down this formula for strains, and you find local strains epsilon 1, epsilon 2, gamma 1, 2 over 2. Whenever you are applying transformation formula, you need to use this tensorial strain, gamma over 2, instead of gamma, because transformation formulas are applicable for tensorial strain, gamma over 2. This is the transformation matrix times strains, or strain matrix, epsilon y, epsilon x, epsilon y, gamma xy over 2. But this result is in terms of gamma 1, 2, not gamma 1, 2 over 2. And to be able to deal with this, we introduce a new matrix, introduce the Reuter matrix at this point. And this is designated as R. It's equivalent to this matrix, it elements 1, and another one on the diagonal. This term is 2. This is called or named as Reuter matrix. And if you multiply strain vector by Reuter matrix, for example, R times epsilon 1, epsilon 2, gamma 1, 2 over 2, you get epsilon 1, epsilon 2, gamma 1, 2, the shear strain on the right side. this term is found, epsilon 1, epsilon 2, gamma 1, 2. Therefore, we have written this epsilon 1, epsilon 2, gamma 1, 2. It's R times this matrix, R times epsilon 1, epsilon 2, gamma 1, 2, over 2. However, I'm going to replace it by this form, epsilon 1, epsilon 2, gamma 1, 2 over 2. Local is T times global. So I replace it. Therefore, this is written as T times epsilon X, epsilon Y, gamma XY over 2. And I can use Reuter matrix one more time to replace this with full engineering strain. In other words, you can rewrite this result, or I'm going to rewrite this as R times T epsilon X, epsilon Y, gamma XY over 2. From this definition, it follows that this is equivalent to R inverse times epsilon X, epsilon Y, gamma XY. Therefore, this will be equivalent to R inverse times epsilon X, epsilon Y, gamma XY. And the right side was the local strain, epsilon 1, epsilon 2, gamma 1, 2 over 2. Let's say that this is equation suppose that this is 4 sigma equals T inverse Q epsilon. This is 4 and this is 5. Which means that we will substitute 5 into 4. This one. Epsilon 1, epsilon 2, gamma 1, 2 is written in terms of epsilon X, epsilon Y, gamma XY, and substitute 5 into 4 to find in this final form. You go back to 4 sigma X, sigma Y, tau XY equals T inverse Q epsilon 1, epsilon 2, gamma 1, 2. In other words, you have sigma X, sigma Y, tau XY equals T inverse times Q times epsilon vector, which is going to be replaced by this result 5. Therefore, we add here R T R inverse times epsilon x, epsilon y, gamma x, y. So a number of matrices, 5 matrices are involved here. This is the final result, but we'll simplify this further. This is an important result, but we can simplify it further. We are going to define a new matrix. Let Q bar be equal to this product. Let's say that this is Q bar. Now, for Q bar is T inverse Q R T R inverse. And this is a transformed matrix. This matrix is valid in the global coordinate system. It's called transformed reduced stiffness matrix. Reduced stiffness matrix. And the shorthand notation compact notation for this result is sigma x, sigma y, tau x, y equals Q bar epsilon x, epsilon y, gamma x, y. And this result is valid in the global system. Recall that at the outset we have defined these global system for the angle lamina and the local system. And for Q bar depends on this angle of inclination. Theta. But we can carry out a simplification to find the elements of Q bar. And this is done symbolically by a math package. You can use either MATLAB or Maple. The computations are shown in file 4.3 .pdf at the website. And I'm going to talk about this computation. This is file 4.3. It shows how the elements of Q bar matrix are found symbolically. You have to define all matrices. This is just a matrix multiplication, but you have to correctly define all matrices involved. We start with T, transformation matrix. All elements are defined in terms of theta. This TH is theta now. I have here defined transformation matrix. Define the inverse of this, T inverse. I did not invert it symbolically. I have defined the inverse in terms of the elements. T inverse. What are the required matrices? Q matrix. This is the stiffness matrix in the local system. It's defined in terms of its elements. Reuter matrix R is also known. All of them are defined. And K-out matrix multiplication. You would like to find Q-bar matrix elements of the Q-bar matrix. And what is Q-bar matrix equal to? This was our definition, T inverse times Q times R times T times R inverse. This is our definition. Now I'm carrying out a multiplication, or these multiplications symbolically. And Q-bar matrix is actually obtained once you use this, or once you make this definition. Q-bar is obtained, and simplify the elements of Q-bar matrix. For example, Q-bar 1, 1 is this Q-bar element 1, 1, and I'm using an expand comment here for simplification, and it's going to print out the element in explicit form. This is our first element, Q-bar 1, 1. Q11 cosine 2, 4, theta 2 cosine squared theta sine squared theta Q12 plus the additional terms. Now, Q-bar 1, 2. The entry 1, 3 is named as 1, 6 because of our original definition for 6. I'm going to write these, but some of them at least, but these are the results. Q-bar 2, 2, 2, 6. This is the element 2, 3, 6, 6, the element 3, 3. All of them are found. Prove that this is indeed a symmetric matrix. It's symmetric. Transformed matrix is also symmetric. And this operation proves that it's symmetric. Simplify Q-bar 2, 1 minus Q-bar 1, 2. It should be equal to 0. It's shown that this matrix is symmetric. The transformed matrix is symmetric. And we have obtained all elements of the Q-bar matrix symbolically by Maple. So that's the Maple worksheet. But you can do this by MATLAB as well. And you can use this in further computations regarding angle lamina. Any questions about these results? So let me summarize our findings. I have shown how the elements of this matrix Q-bar are calculated by Maple. Therefore, Q-bar is a fully populated matrix. The transformed reduced stiffness matrix is a fully populated matrix. None of the elements is 0 now. You have Q1, 1 bar, Q1, 2 bar. This is named as Q1, 6 bar, 1, 3. That's notation. Q2, 2, 2, 6. Q6. Symmetric matrix, we have shown that it's symmetric. And the elements are found in terms of the entries of stiffness matrix, reduced stiffness matrix, and Lamina angle. For example, all of them are given in the book and in the Maple file, but for example, Q1, 1 bar. This was found as Q11 C to the 4th plus Q2 S to the 4th plus 2 times Q12 plus 2 Q6 C squared S squared. This is Q11 bar. Written in terms of the Lamina angle, this means cosine theta to the 4th and elements of the reduced stiffness matrix in the local system, Qij. Recall that Qij are the elements of this reduced stiffness matrix. And all entries are Germans, for example. So you should be able to find these Q1 2 bar up to Q6 6 bar. For your information, let me write this as well. Q6 6 bar is Q11 plus Q2 minus 2 Q12 minus 2 Q6 C squared S squared plus Q6 times C to the fourth plus S to the fourth. All elements are therefore found. What is matrix? Now, find the elements yourself using MATLAB or Maple, which means that define all these matrices in the Mat software, T inverse Q reduced stiffness matrix in the local system, Reuter matrix, T, and R inverse. And carry out this matrix modification, simplify the entries, and write down the elements one by one. They are actually given in the book and in a Maple file. They're already given, but try to derive these yourself. And once this matrix is available, you'll be able to examine these problems. A Lamina will be given. And the fibers are going to be inclined now with respect to the global axis. And these are the global axes. And we mentioned at the outset that the equations of orthotropy are valid in the local system. Thus, this is X and this is Y. This is 1 and this is 2. The Lamina angle is an important parameter here. And you will be given stresses acting in the global system. For example, stress in X direction can be given. If this is known, you can apply this formula or the inverse of this formula to find strains, for example, in the global system. And those are going to be global quantities, but you will also need the local quantities in composite analysis, because failure theories are written in terms of the local quantities. We will talk about this, but all variables, stresses, and strains in the global system can be calculated by using the main relation. And stresses and strains in the local system can be calculated by transformation. We have talked about transformation formula, and then you'll be able to apply them for different types of failure theories. Any questions about this final result? or the entries of the transformed reduced stiffness matrix. Any questions or comments? I'm going to stop recording if you don't have any questions.